So we're in section 4.3, the addition rule for probability. And again, just check yourself. What is that key word that you're going to look for to associate with the addition rule? That key word is or, right? If there's probability of A or B, one thing or the other, that gives you an idea that you're going to be adding or using the addition rule for probability. And here's a deck of cards. It consists of these types of cards. Let's consider face cards as only Jack, Queen, King. And here we go. What is the probability that the card is an ace or a jack? An ace or a jack? Well, we have how many aces? There's 4 aces out of a total of 52 cards. And there are 4 jacks out of a total of 52 cards. Are there any cards that are aces and jacks? No, there aren't. That means these two events are mutually exclusive. And so the probability would be finding the probability of an ace plus the probability of a jack, 4 50 seconds plus 4 50 seconds, or 8 50 seconds. Let's go back to the other one now. Number 2. What is the probability that the card is an ace or a heart? Well, we have an ace. There are 4 aces. Or a heart. There are 13 hearts. That's the third row there. Ace of hearts, 2 of hearts, and so forth. Is there an overlap in between these two events? Getting an ace and getting a heart. Yes, there is. The ace of hearts would be counted twice. And therefore, I would have to actually omit one of the cards. The probability of getting an ace, there's 4 aces. The probability of getting a heart, there are 13 out of 52. And then minus the probability of getting an ace of hearts, which would be 1 52nd. And so the probability in that case would be 16 52seconds. Okay? So that's, again, this difference between having an intersection and not having an intersection. And again, please note in this here, when you were reading this, do you see this keyword or? Do you see this word or? Again, that gives it away that you're supposed to be using the addition rule. Okay, toss a coin 3 times and observe all possibilities of the number of heads. Now this is a little bit different. All possibilities of the number of heads. Toss a coin 3 times and you can get 0 heads, right? You can get one of the tosses would be end up a heads. You can have 2, you can have 3 heads out of 3 coin tosses. And you can actually create a probability distribution because these are all the possibilities. You flip a coin, you can 3 times, and you can have 0 heads, 1 heads, 2 heads, or 3 heads. Here's the sample space. The sample space we've seen already for 3 coin tosses. And then the question is, well, we want to figure out what is the probability of getting, I want to add all the probabilities up. What is the total probability? Well, since we're dealing with entire sample space, you would have the total probability to be equal to 1, right? What's the probability of getting 0 heads? That's 1/8. Where is this 0 heads? This one right here has no heads, right? It has 3 tails. What's the probability of getting 1 head? Well, 1 head would be, exactly 1 head would be this one, and this one. There's 3 of them. What's the probability of getting 2 heads? HHT, HTH, and THH. That's 2 heads. So there's 3 of those, 3/8. And then what's the probability of getting getting all 3 of them to be heads? There's 1/8 probability. And if you add up all these probabilities, they will always equal 1. And this is something called a probability distribution. Here's a table of 0 heads, 1 heads, 2 heads, or 3 heads out of 3 coin tosses. And the probability distribution is a table of all possible events along with the probability of each event. The sum of all the probabilities must equal exactly 1. If it doesn't, then what you have in front of you is not a probability distribution. Please note the events are mutually exclusive, right? Events are mutually exclusive. So here's another example. Roll a dice and observe the sum of 5. We have a sample space of 36 elements, right? If we roll 2 dice, a pair of dice, we have 1, 2, 2 threes, 3 fours, and so forth. And so if we're going to construct the probability distribution, it would look like something like this. If you get a sum of 2, right? How many 2's do we have? Well, we have 1 out of the 36. If we have a sum of 3, well, you can get that 2 different ways. Let me show you that picture one more time, right? Erase these green and red circles and take a look at what we're being asked. What's the probability of getting a 2? There's only 1 2 out of a total of 36. What's the probability of getting a 3? There are 2 3's out of a total of 36. What's the probability of getting a 4? There are 3 fourths, and so there are 4 5's, there are 5 6's, there's 6 7's, and so forth. If you add up that entire probability, all those possibilities, they will have to add up to the number 1, 100%. Okay? So that's constructing a probability distribution. Let's talk about contingency tables here at the end of this section. A contingency table has rows and columns, and then we can find out probabilities based on the totals. A lot of times you will not have these grand totals over here and over here. And I'm sorry for the slide here. Looks like the columns have been moved over to the right by my PDF for some reason. But you guys can see the columns and what the numbers pertain to each column. So let's let the event A be select a man, and let's let B be select a girl, right? So what's the probability of randomly selecting, this context is Titanic mortality. There are 2,223 people. Some of them didn't make it, some of them made it. And we're looking at what is the probability of getting an A or a B? What's the probability of randomly selecting a man or a girl? Well, what's the probability of selecting a man? There's 1,692 men that were on the Titanic out of 2,223. And how many girls were there? There were 45 girls out of 2,223. And so because notice that there is no overlapping in this contingency table between men and girls, right? Then we have mutually exclusive events. And because we have mutually exclusive events, there's no double counting. Therefore, we just add the two probabilities and get 0.781. Okay, that's the example of no overlapping. Let's take a look at when there is overlapping and we have an or statement. Let's let the event A, same table, contingency table. Let's say event A is a woman, and let's let event B be select someone who died, right, who didn't make it. Well, if you take a look at this and you want to look at all of the people that died, right, there's 1,517 people that died, and there are 422 women, and 1,517 who actually died. Do you notice that these two events or sets actually overlap? And their overlapping is 104. So there was 104 women who died on the Titanic. That was counted twice, right? Once within the number 422, and another time when I counted 1,517, right? To get 1,517, I added 1,360, 104, 35, and 18. So I had to subtract one copy of 104, and I get my probability to be 0.825. So adding the total probabilities and subtracting their intersection, dividing by the total number of people that were on the Titanic. And this is an example of not mutually exclusive events or sets. And please note again that I will have something either like a contingency table or some way that I'll be testing you guys on, making sure that you guys understand what mutually exclusive and not mutually exclusive sets are, and finding the probabilities, okay? If I were going to make a probability distribution from this contingency table, what would it look like? Well, one thing that we could do would be just look at all of the columns, right? Men, 1,692 out of 2,223. Women, 422 out of 2,223. And so on, 64 and 45 for boys and girls respectively. If I add this column up of probabilities, since this is a probability distribution, what does this column have to add up to again? You're right, the number 100% of the probability. And that's why it's called a probability distribution. 100% of the probability has been distributed a certain way, this way, right? Or 100% of the probability is there, and we've allocated some of the probability to this category, men. We've allocated some of the 100% probability to this category of women, and so forth. Okay? So keep that in mind. That's what a probability distribution means. It's a distribution of 100% of the probability. Here's some more contingency at the very end here. We've heard about lie detectors, right? Polygraph test. And so here are some results for a polygraph test. During a polygraph test, this row stands for polygraph said that they lied, right? And then we actually found out that some did not lie and some did lie. So if polygraph said that they lied, notice that there are more that the polygraph caught that did actually lie. And the polygraph said that they didn't lie and they actually did not lie. There's 32. And then when the polygraph said that they didn't lie and they actually lied, right, they weren't caught, there's 9 total. And then the numbers outside of the tables, columns, and rows are the grand totals. And then the question is, so find the probability of picking a subject who lied or who the polygraph said that they lied, right? So subject who lied. Well, subject who lied would be this second column here. That gives me a total of 51. And then polygraph said that they lied. Well, polygraph said that they lied. That would be this first row. So it looks like I'm adding this second column and this first row. And do you see that there would be an overlap of 42? The number 42 would be double counted when I'm counting the column and when I'm counting the row. So you can go about this one of two ways. Either double count 42 and subtract 1 copy, or just don't count it twice, since you see that you have something in the intersection. Okay? And so that answer would look like this. You would take 57, which is the row total of the first row, plus 51, which is the column total of the second column. Subtract 1 copy of 42 98ths, because there's a total of 98 people that went through this, and you get your total. So again, if there is an intersection, subtract 1 copy of the intersection. I hope that helped you understand a little bit more about the OR statement. Again, OR is associated with the addition rule. Let's take a look at the multiplication rule in the next section.